thank you very much. Thank you very much for coming. Thanks for inviting me. Thanks to ICOR. And I want to talk about something very different from the previous talk, and specifically focus on what's the right strategy for moving beyond today's data centers. So this is recent work with Ankit Singla and Simon Kassing from ETH, and with my students Gal Shakov and Asaf Aladarsky at Hebrew University. And this appeared at SECOM 17. And let me start with the basics. So what's a data center? I'm sure a lot of you know, but a data center is a network that interconnects a lot of servers. They can be small, they can be huge, right? Underlying every Google service, Amazon service, Facebook hides a huge data center for computing the computation this involves. And for this reason, optimizing data center performance and identifying the right data center architecture has been a very prominent problem in networking research for nearly a decade, I think. So what do today's data centers look like? So at a very high level, they have many names. So this structure has many names, clause networks and fat trees, et cetera. But at a high level, it's a multi-rooted tree where the server racks are at the bottom, and above the server racks, we have switches that are interconnected to other switches that are interconnected to another layer of switches. And it may not be as simple as this, right? So this is a diagram of Facebook's data center, right? But the high-level idea is the same. It's a multi-rooted tree that is designed in complex ways, perhaps to address cabling concerns, et cetera, but this is the high-level concern. And one unifying theme in a lot of the studies we've seen about what traffic characteristics within data centers look like is that they're skewed to the extent of being very highly skewed. So for example, studies out of Microsoft indicate that most of the time, only 1% to 40% of the servers are actually communicating. So how does one contend with the fact that traffic patterns might be unpredictable and we're not sure which servers are going to communicate, but we know that maybe not a very large fractions of the servers are going to communicate? So one way to deal with this is to just throw capacity at the problem. Just build a large-scale clause network, fat tree, data center, right? That can accommodate different traffic patterns because it has sufficient capacity to do so. The problem is that this is expensive. And for that reason, this is not what people typically do. What people typically do when designing data centers is they oversubscribe. So let me give you an example that isn't realistic, but is actually very illustrative of oversubscription. Say that I were to remove one of the 4 upper switches and all of its incident links, right? What would happen? I would remain with 75% at least, right, of the capacity. But here's an interesting observation. Even 50% of the servers trying to communicate with each other are bottlenecked in this example. Right? So this is sort of a...
Links are bottlenecked.
I'm sorry?
Links are bottlenecked.
Yeah, the communication is bottlenecked when only 2 pods are trying to communicate. Right? And this is actually the good news. So the bad news is...
How many bottlenecks when there's 100%?
So now it comes to the question of how much throughput you can support. Right? You can support everything.
After you remove the quarter, how much was it before you removed the quarter?
All of them. So this was non-blocking. Right? So you removed 25% of the capacity, but you were bottlenecked at 50% of the servers. Right? And this actually gets worse. So if you look at larger fat trees, so for example, K means the number of ports per switch. Right? If you look at large switches, right, still 2 pods communicating with 75% of the capacity remaining intact are bottlenecked. Right? So this is an issue. And for that reason, we've seen a lot of work in the past decade on trying to investigate a natural approach to this problem. I was actually surprised by how many such papers there are. So each and every year, there's at least one such paper, typically more at the top networking conferences. Right? And what's the high-level approach? The high-level approach is, let's change the topology dynamically. So at a high level, so these are the server racks. Let's identify highly communicating pairs, and then let's do applied physics magic to interconnect them directly. Right? So what can applied physics magic look like? It can look like this. Right? This is a recent proposal for Microsoft using disco balls, right, to actually interconnect things in real time. Right? But there's many different approaches for doing this, but the high-level scheme is similar, right, which is identify highly communicating pairs and interconnect them, right, directly. And of course, this comes with many challenges. Some of them are technological challenges, some of them are monetary, some of them are operational challenges. And two foundational questions that we wanted to explore were, one, what rigorous benchmark should we be using? Right? In the sense that fat trees seem like the easiest static topology to pick on. Right? They're ideally inflexible. Right? And the second is, what is the utility that can be derived from dynamically moving links? Right? So this is just one comment about this, right? Obviously, anything you can do with a static topology, you can do with a dynamic topology. So this isn't the right question, right? You can just fix the dynamic topology. The point is that dynamic ports are more expensive than static ports. Right? A factor of 2x is actually, or 1.5x is conservative. So you're not comparing dynamic topologies to static topologies. You're comparing smaller dynamic topologies to larger static topologies. Right? The question is, what's the right trade-off? Right? So first, let me try to hand wave a formalism. Right? And please look at the paper, because I'm really going to hand wave this. But here's a potential definition of a benchmark, of a rigorous benchmark. Now, for simplicity, think about all-to-all traffic patterns. Everyone wants to talk to everyone, right? So we have link capacities 1, the demands are 1, right? And we just want to send traffic through the network. And we care about how much traffic what's the throughput that all servers can achieve simultaneously, right? So alpha means every server, is able to send alpha units simultaneously. Right, now let's assume, so look at this graph. This is the fraction of servers with traffic demand. So 1 means everyone wants to talk to everyone. 0.5 means there's half of the servers that want to communicate with each other. Right? Within this 50% of servers, each server wants to communicate with each other server. And 0 to 1 here means how much throughput, right? What's the alpha that they can achieve? So let's assume that when everyone communicates with everyone else, the throughput per server achievable is alpha. So I'm going to draw a line here for a potential benchmark. Let's also assume that when alpha % of the servers are communicating, they can actually communicate everything. Right? Then the throughput is 1. And in between, we want things to degrade gracefully. Right? So we have this line saying if an X fraction of the server are communicating, then each server can push out alpha over X fraction of traffic. Right? Notice that at the endpoints, this is exactly right. Right? So this is alpha here and 1 there. Right? Yeah.
This is kind of assuming that they talk randomly to other people.
Okay, so
There's no structure inside the...
So what is this assuming? So right now in this talk, right, I was talking about all-to-all. So they're not talking randomly, but for this illustrative example, there's 50% of the servers, and they all want to talk to each other. Right? So every I and j has dij equals 1. Right? But I don't think it's limited to that. So actually in the paper, we showed that this is an upper bound on the flexibility you can achieve for different traffic matrices. And we even conjecture that this is a general phenomenon. I think that there's an interesting theoretical question there, right? That it might be that for the proper definition of what a class of demand matrices means and what it means to project a class of demand matrices on a subset of the servers, this is the best you can achieve, right? So anyway, we'll be using this as a theoretical benchmark, and for some of the distributions we use, we know it is an upper bound on what you can achieve. So we call this throughput proportionality. And it turns out, as I showed you, that fat trees are, in a sense, the worst possible static topology you can come up with, because if you support alpha when everyone is chatting, right, you still support alpha when more and more network resources become available. You have less become available to the chatters because we've removed other chatters. So the question is, are there flexible static data center networks that do better? And the non-surprising answer from a theoretical perspective, right, is that, of course, there are expander graphs. How many of you are familiar with the definition of an expander graph? Okay, so I'll linger on that for a little while, but let me tell you the high-level idea from a data center design perspective. Instead of having a rigid layered connectivity, as in a fat tree or a closed network, the idea is to have something that's more flat, right? It can still be clustered, right? But it's flatter. Each and every switch is a top-of-rack switch. Under each switch, we have servers. There's no switches that we just use as relays. And actually, in the past few years, we've seen several proposals for modern-day data centers, as proposals for new designs for data centers, that implicitly or explicitly were expanders. So here's the high-level definition of expansion. So there's various definitions of expansions. I'm going to focus on edge expansion because it's the easiest to grasp and the most relevant from our context. We have a set of switches S. I've partitioned my network into a set of switches S and the rest of the switches in the network. Okay? So what we have here is the capacity, the number of links interconnecting my set of switches S with the rest of the network. Now consider this expression. What this expression captures is the average outgoing number of links traversing the path. So the edge expansion of a graph is simply the worst case such value. Still with me? Okay, so intuitively this captures something really simple, which is I want to look at the worst case outgoing capacity from a set of switches to the rest of the network across all possible partitions of the network. Right? And also intuitively, this is a very important value because it's closely correlated with the extent to which traffic can be bottlenecked, right? If there's no bad cuts, right, then intuitively a lot of traffic can flow through the network. Same goes for fault tolerance, right? The number of paths I have available. So expanders are graphs with high edge expansion. What's high? So it's quite easy to show that you can do better than d over 2 if the graph is deregular, that is if every node has degree d. Right? And you can actually get very close to d over 2. And there's a lot of research on deterministic constructions. And actually, a paper that we published last year was exactly aimed at leveraging these deterministic constructions of expanders to present something that's cabling friendly that we believed we could actually get deployed. And this is something that we're still promoting. Back to our question. So now we have a candidate topology, right? So back to our question, how valuable is the ability to move links around? So again, think of the traffic as highly skewed, right? So 30% of the servers want to communicate, maybe 1%, maybe 40%. Then what you get intuitively in a flow model looks something like this, right? A fat tree, as I said, is ideally inflexible. So regardless of what fraction of the servers want to communicate, notice that this starts at 10%. This is where you don't see the just go up near zero, right? But regardless of what fraction of the servers try to communicate, right, this is constant. And you can do more, you can do better with dynamic networks. Delta means the cost per port. So once again, we're comparing, if the cost is 1.5, right, that means that a static network could have 3/2 times that many nodes. Right, so again, we're comparing larger static networks to smaller and dynamic networks.
So here the lines are, the orange line means 2/3 of the number of edges?
The orange line means that this comparison, okay, let me tell you what the orange line means. It means that the factory network we're comparing to is 1.5 larger
In terms of number of links?
in terms of number of nodes. In terms, or more accurate, no, actually you're right, in terms of number of ports translating to both links and switches, right? How many switches you need to support that many links. But you're right, it exactly translates to links. And interestingly, this is what an expander graph would look like on this plot, right? And the thing I want you to keep in mind is this, right? That the domain of interest here is actually, even interestingly, in the papers advocating the dynamic topologies, right? Even in the distributions they use, this is the domain of interest, right? Because these are the same papers often coming out of Microsoft. And interestingly, now that we have a candidate upper bound, and in some cases it is an actual upper bound, I mean provably an upper bound, we know that we're not very far from the best that is achievable. So this was the flow model. What about experiments? So we've conducted a lot of experiments, and I'm not going to belabor you with the experiments. Let me just give you a high-level idea.
Ask a question?
Yeah, of course.
Can go one. So this is for a specific dynamic network. It's not all dynamic networks.
So we have an
dynamic factory. What is that?
no. So we've tried to abstract away from the model of dynamic networks, and to give the dynamic network the ability to, right? Because the high-level idea across all these topologies is the same, right? That is interconnect things. Anything that does that, and we actually didn't take into account things that might actually worsen performance, like configuration delays, like queuing and things like that. But anything, even under ideal conditions, right, could not do better than this. That was truly an upper bound on what could be achievable by something of this flavor. So we've ran experiments comparing a full bisection bandwidth fat tree, with n being the number of switches equal 320, to a smaller expander graph. And if you're interested in, one of the things that we were aiming for is not comparing dragons with unicorns, right? That is not saying, okay, there's dynamic topologies, but they might not be feasible in practice, so we're going to compare them to another network that might not be feasible in practice. So one of the things we were aiming for is utilizing tools that people know and understand. Right? And this is why at the servers, what you see here are two things that are actually used in practice, DC-TCP and flowlet routing. In the factory, we use ECMP. In the expander, this is an important point. Those of you who are familiar with ECMP, what ECMP basically means is routing along shortest paths, right? And spreading traffic more or less equally between them, right? This is not going to work in an expander graph, because the whole point of an expander graph is that it gives you more path redundancy and more path diversity, right? So if you don't utilize that, so think of a world where there's two switches that want to communicate and they're directly connected, and they're the only ones that want to communicate. Clearly, you should better utilize the network than just sending traffic along the single link interconnecting them, right? So one thing that we propose, and seems to well approximate the flow model, is a hybrid scheme where until a flow passes a certain limit, you send it along shortest paths, right? Once it passes a certain limit, you do valiant load balancing, right? You choose an intermediate node at random, you route along the shortest path to that intermediate node, then you route along the shortest path to the final node, to the destination. And let me give you some intuition for why this makes sense. If everyone wants to talk to everyone, I should be routing along shortest paths. Right? I don't want to cause contention in the network by sending along long routes. If only I want to talk to someone else, I should be using variant load balancing. Right? I should be spreading traffic as much as I can. Right? This sort of captures the intuition that you can't just choose one of these and have it be fixed across everything, all traffic patterns. Right? You somehow need some level of adaptation. I think that there's a lot of theoretical questions hiding there.
So the threshold is individual or global?
So the threshold in our experiments is global, and it's a very good question of how one would define this threshold in an online manner. It is based on the traffic characteristics you see, because this threshold is intended to capture the distinction between I'm sending a lot and I don't send a lot. I'm sorry?
If it's global, it's we send a lot.
So
We send a lot, right? Yeah, exactly. The borderline between small and large.
So all the flows are going through the same routing, so ECP or hybrid?
Yeah. So hybrid contains both. They all, every switch individually, right, at the,
ECP or VLB?
or VLB, yeah. So we've looked at many traffic scenarios. So when trying to evaluate such a thing, there's a lot of parameters, right? There's who's talking to whom. There's how large are the flows. There's what's the flow inter-arrival time. Right? So we've experimented with a lot of different patterns, both empirical and contrived, just to look at the results we get. This might be the most interesting one because this is the proposal out of Microsoft. So we use their own traffic distribution to make our case. Right? And we look at different flow arrivals time that also, some are contrived and some are actually modeled after real workloads in data centers. Please look at the paper for the concrete results, but this is our take-home messages. One is that Expander achieves comparable performance to non-blocking fabrics at a lower cost, that is 2/3 or less. And so this is a way to achieve both flexibility and a much lower cost than just providing fully non-blocking. And the other one is that it matches the performance of dynamic topologies even in the environments for which these were designed. And what this teaches us, I think, is that there is a much easier way beyond today's data centers than going all the way towards dynamic topologies, at least at this point in time. So our high-level point is that expanders are the static topology benchmark, and a dynamic topology, to prove useful, must contend with that benchmark. And what that means is that demonstrating the advantage of a dynamic topology means comparing to expanders at an equal cost, right? Using sufficiently expressive routing. And as I said, we gave dynamic topologies the benefit of the doubt in terms of reconfiguration times, et cetera, but just assuming that there are none. Right? But obviously, you have to take that into account. So what are we working on now? Better oblivious routing schemes. Can adaptive routing help? Right? So we've done something that's very simple, but what should routing on expanders actually look like? And what information about the traffic pattern can I take into account? And the last thing, of course, is deploying this thing. So we're doing several things along these lines. So we're working with a large switch vendor, and we're also building an experimental platform at Hebrew also for evaluating this platform. And hopefully a year from now, we'll know more. Thank you. Sure.
Why did you put oblivious for the routing?
So
The hybrid is not oblivious.
you're right. So one of the things that we're very interested in is learning to what extent we are dependent on information. So it could be oblivious, it could be semi-oblivious, it could be that the size, right, the average size of the flow is what we care about. These things have important implications, right? So we're not, for example, this model where you can distinguish between flows based on simple to gather aggregated statistics is something that's not oblivious and not semi-oblivious, but you can actually see why it would be both theoretically interesting and useful in practice. It seems like there's we don't fully comprehend at this point what information is needed. We know that you don't need to know the demands, for example, but what is it that you do need to know?
I took over its slides.
Good.